So hello, good morning. We have here hydrogen for industrial gases. Hydrogen or H2 is derived almost exclusively from carbonaceous material, primarily hydrocarbons and or water. These materials are decomposed by the application of energy, which may be electrical, chemical, or thermal. Examples include electrolysis of water, steam reforming of hydrocarbons, and thermal dissociation of natural gas. Hydrogen is also produced by partial oxidation of hydrocarbons and by such less important method as the steam iron process, water gas and producer gas processes, and separation from cook oven gas and refinery of gas streams. Diffusion through a palladium silver alloy furnish very high purity hydrogen. And for the uses and economics of hydrogen, hydrogen has long been an important gaseous raw material for the chemical and petroleum industry. The annual product of merchant hydrogen is in excess of 3 times 10 to the 9 cubic meter and is only a very high part of the total industrial production. Table 7.2 gives the hydrogen requirements for making some typical chemicals. Hydrogen is sold as gas and liquid. Liquid hydrogen is the most profitable, is produced by only three companies, and is shipped by tank car, truck, or bark. Gaseous hydrogen is made by many companies and is shipped in tube trailer holding about 4,300 cubic meter. The use of metal hydride as hydrogen sponges is increasing for storing hydrogen compactly at moderate pressure. That is 2 megapascal compared with 14 megapascal of the common compressed hydrogen cylinder. The hydrides used are alloys of magnesium nickel, iron titanium, lanthanum nickel, and misched metal nickel. And for the electrolytic method of hydrogen, the electrolytic process produces high purity hydrogen and consists of passing direct current through an aqueous solution of alkali and decomposing the water according to the following equation. The theoretical decomposition voltage for this electrolysis is 1.23 voltage at room temperature. However, because of the overvoltage of hydrogen on the electrodes and also cell resistance itself, voltages of 2 to 2.25 voltage are usually required. A typical commercial cell electrolyzes 15% NaOH solution, uses an iron cathode and a nickel-plated iron anode, has an asbestos diaphragm separating the electrode compartments, and operates at temperature from 60 to 70 degrees Celsius. The nickel plating of the anode reduces the oxygen overvoltage. Most types of cell produces about 56 liters of hydrogen and half as much oxygen per megajoule. The gas is about 99.7% pure and is suitable even for hydrogenating edible oils. The cells are of two types. So we have here the two types of cell. First is the bipolar or filter press type, and the second one is the unipolar or tank type. So first, the bipolar or filter press type, where each plate is an individual cell, and the unipolar or tank type, usually containing two anodes compartments with a cathode compartment between them. The unipolar cells may be open or closed tank. In most installations, the oxygen produces is wasted unless it can be used locally. Hydrogen is also obtained from other electrolytic processes, for example, electrolysis of salt brine. So for the steam hydrocarbon reforming process, in this process consists of catalytically reacting a mixture of steam and hydrocarbons at an elevated temperature to form a mixture of hydrogen and oxide of carbon. The following basic reaction occur. Although the equations are shown for the general case of any hydrocarbon feed, only light hydrocarbons have been successfully used in commercial practice. Natural gas is most common and propane and butane or LPG are also frequently used. With the use of the specially prepared catalyst, naphtha is also a suitable feedstock. This first reaction is the reforming reaction. It is highly endothermic and the most product exceed the moles of the reactant, so the reaction goes to completion of high temperature and low pressure. Excess steam is normally used. Although the basic purpose is to prevent carbon formation, it also helps force the reaction to completion. So for the second reaction, it is the water-gas ship reaction. It is mildly exothermic and is favored by low temperature but unaffected by pressure. Excess steam also forces this reaction to completion and is so used. A catalyst is usually employed. Both these reactions occur together in the steam reforming furnace at temperature of 760 to 980 degrees Celsius. The composition of the product steam depends upon the process conditions, including temperatures, pressure, excess steam, which determine equilibrium, and the velocity through the catalyst bed, which determine the appropriate approach to equilibrium. A typical product contains approximately 75 hydrogen, 8% CO, and 15% carbon dioxide. The remainder consists of nitrogen and unconverted methane. For the production of additional H2 or hydrogen, the reformer is followed by a separate stage of water-gas shift conversion. Additional steam is added and the temperature is reduced to 315 to 370 degrees Celsius to obtain more favorable equilibrium condition. A single stage converts 80 to 95 of the residual CO to CO2 and hydrogen. Because the reaction is exothermic, the reactor temperature rises. This enhances the reaction rate but has an adverse effect on the equilibrium. With high concentration of CO exists in the feed, the shift conversion is usually conducted in two or more stages, with interstage cooling to prevent an excessive temperature rise. The first stage may operate at high temperatures to obtain high reaction rates, and the second at lower temperature to obtain good conversion. We have here on the next slide is the figure 7.3. This is the process using propane and the material requirements are listed in table 7.3 on slide 11. So this process can be broken down into the following coordinated sequences. So now we have here the process using propane. First, we have the propane is vaporized by steam. Next is the propane vapor is desulfurized by contact with activated carbon to prevent the activation of the catalyst. Next, the propane vapor mixed with steam is reformed over a nickel catalyst at about 815 degrees Celsius in alloy tubes in a combustion furnace. This is to furnish the heat for this endothermic reaction. Next one, the gases hydrogen, CO, and some CO2 are cooled to about 370 degrees Celsius and the partial pressure of water increases by addition of steam or condensate and pass over an iron oxide catalyst in the first stage CO converter, where 90 to 95% of the CO is converted to CO2 with more hydrogen. This is the so-called shift or water-gas conversion reaction. These hot gases are first cooled by heat exchange with the gases leaving the first stage CO2 absorber before entering the second stage CO converter and finally by water to about 38 degrees Celsius. Next one, the cooled gases are scrubbed with monoethylamine solution in the first stage gear bottle absorber to remove essentially all the CO2. Following this, the gases heated by exchange with the gases leaving the first stage CO converted are passed through the second stage CO converter, also followed by the second stage CO2 absorber. The gas low in CO2 and CO are heated to about 315 degrees Celsius by exchange with gases from the second stage CO converter and passed to the methanol over a nickel catalyst to convert essentially all the carbon oxide to methane by reaction with hydrogen. The product hydrogen gas from the methanol is cooled to 38 degrees Celsius with water, leaving it pure except for saturation with water vapor. The lean amine solution from the gear bottle reactivator is first pumped through the second stage CO2 absorber to reduce the CO content of the hydrogen gas to a minimum and then pumped to the first stage CO2 absorber to remove the bulk of the CO2 in the H2 in the gas. The rich solution is returned to the reactivator through heat exchanger and the CO2 is stripped over by steam. And the CO2, about 55 kg over 100 cubic meter hydrogen, can be recovered for sale or used. So this is the table 7.3, the materials requirements for the process using propane as what I have mentioned earlier. And for the catalyst, in many reactions connected with hydrogen manufacture, various catalysts are necessary. For example, we have here the nickel for steam hydrocarbon reforming as what I have mentioned earlier. Next one is the iron oxide for CO conversion or the shift reaction, and the nickel for ammonia cracking or dissociation. So we have here the next one is the partial oxidation processes. This rank next to steam hydrocarbon processes in the amount of hydrogen made. They can use natural gas, refinery gas, or other hydrocarbon gas mixture as feedstocks. But their chief advantage is that they can also accept liquid hydrocarbon feedstocks such as gas oil, diesel oil, and even heavy fuel oil. There are three commercial versions of the process. It was originally developed by Texaco, and variations were introduced later by both Shell and Montecatini, which differ primarily in the design and operation of the partial oxidation burner. All employ non-catalytic partial combustion of the hydrocarbon feed with oxygen in the presence of steam in a combustion chamber at flame temperature between 1300 and 1500 degrees Celsius, when methane is the principal component of the feedstock. The reaction involved are the following. The first reaction is highly exothermic and produces enough heat to sustain the other two reactions, which are endothermic. The next slide is the net reaction is as follows. So again, this is the first reaction where it is highly exothermic and produces enough heat to sustain the other two reactions which are endothermic. This is the net reaction as you can see in this slide. So this reaction is exothermic and so the overall process is a net producer of heat. For efficient operation, heat recovery using waste heat boilers is important. The product gas has a composition that depends upon the carbon-hydrogen ratio in the feed and the amount of steam added. Pressure does not have a significant effect on the composition, and the process is usually conducted at 2 to 4 megapascal, permitting the use of the most compact equipment and reducing compression costs. So as you can see on this table, this is the following composition is the typical for fuel oil feedstock. We have here hydrogen that has 48 mole percent, CO with 46.1 mole percent, CO2 with 4.3 mole percent, and we have here the CH4 0.4 mole percent, N2, etc. or other substances are 0.3 mole percent, and we have here H2S 0.9 mole percent, a total of 100 mole percent. This gas has a much higher carbon oxides or hydrogen ratio than steam reformer gas. In the commercial application of the Texaco process, preheated oil is mixed under pressure with oxygen and preheated steam and feed to the partial oxidation burner. About 26 cubic meter of 95 to 99% oxygen is used per 100 cubic meter of hydrogen with CO produced. The product gas is cooled by a direct contact water quench followed by a water scrubber and a filter. All of the following serve to remove unreacted carbon from the product gas. The carbon is removed from the quench water, for example, by filtering for disposal or reuse, or it may be discarded as a water slurry. The remaining process steps for conversion of the partial oxidation product gas to hydrogen are the same as the steam hydrocarbon reforming process: water gas shift conversion, CO2 removal via monoethanolamine scrubbing, and methanation. So we have here the coal gasification processes. Coal as a source of hydrogen will assume increasing importance in the future as reserve of gaseous and liquid hydrocarbon feedstocks decrease. Although coal was used in early water gas and producer gas plants for the manufacture of a H2CO mixture, these plants cannot compete with more modern processes. The gases produced require the water gas shift conversion and subsequent purification to produce high purity hydrogen. In the next slide, we have there the table 7.4 that show a comparison of the four main processes for the production of hydrogen. So as we can see on this slide, we have here the table 7.4, the comparison of hydrogen production alternative. This is also the comparison of the four main processes for the production of hydrogen. So we have here the cracked ammonia. This is a mixture of nitrogen, 1 volume, and hydrogen, 3 volumes, may be prepared from the cracking or dissociation of ammonia. This mixed gas can be used for hydrogenation because the nitrogen is inert. The process consists of vaporizing the liquid ammonia from cylinder, heating it to 870 degrees Celsius, passing it over an active catalyst, and then cooling it in heat exchangers, where the incoming gas may be vaporized. A single 68-kilogram cylinder of anhydrous ammonia will produce 190 cubic meter of cracked ammonia. This is equivalent to content of about 33 hydrogen cylinders. For the next slide, we have here the hydrogen purification. We have here carbon monoxide removal and carbon dioxide and hydrogen sulfide removal. So for the carbon monoxide removal, it is high concentration of carbon monoxide are commonly reduced by conversion to hydrogen via the water-gas shift reaction. It will be seen again in figure 7.3 on the previous slide. Removal by the scrubbing in solution of complex copper ammonium salt has been used commercially. And for the next removal, we have here the carbon dioxide and hydrogen sulfide removal. Many processes for the removal of the acid gases have been employed commercially. So here in the slide is the monoethanolamine or MEA or Gerbotol process, which I have been mentioned with the previous slide. This process is where a water solution of metanoethanolamine is reacted with CO2 in an observer vessel under pressure at room temp. The MEA solution is then heated and fed to a reactivation column where the MEA CO2 complex is dissociated by stripping with steam at 90 to 120 degrees Celsius and near atmospheric pressure. The CO2 and steam live at the top of the reactivation column and the regenerated solution lives at the bottom. It is cooled and is pumped back to the observer. So as we can see, the chemical reaction involved are here in this slide. Um, Constructed with physical observer type of CO2 removal processes, the MEA process is capable of reducing the CO2 concentration in the process gas to less than 0.1% by volume. A major problem associated with the use of the MEA solution is their corrosive effect on the process equipment. Corrosion is most severe at elevated temperature at where the acid gas concentration in solution is the highest. Control of corrosion is achieved by using stainless steel at potential trouble spot by limiting the concentration of MEA in aqueous solution. In order to limit the CO2 in solution by excluding oxygen from the system and by removing the oxidation and degradation product using the side steam distillation, another system used a corrosive inhibitor, the amine guard, which has greatly decreased corrosion as an operating problem even with increased CO2 loading. So next one, we have here the hot potassium carbonated process. This process developed originally by the Bureau of Mines, in particularly useful for removing large quantities of CO2. Although it can remove CO2 down to 0.1% by volume in the gas being purified, it is generally more economical at purity level of 1% or greater. By absorbing CO2 under pressure in hot solution close to its boiling point and generating it at the same temperature but at near atmospheric pressure, steam consumption is reduced and heat exchanger are eliminated. Process improvement have been obtained through the use of the catalytic addition and promoters to the solution such as in the Gimarco, Vertrocoke, and the catacarb processes. So we have here the next one, physical solvent processes. These are the processes in which CO2 is removed by physical solution in a solvent, which is often proprietary. Example of this class of process are the rectisol process using cold, approximately 60 degrees Celsius methanol, the fluor solvent process using a non-aqueous organic solvent such as propylene carbonate, the sulfenol process using an organic solvent, sulfolane or the tetrahydrothiophene dioxide, the Selexol process using the dimethyl ether of polyethylene glycol, and the Purisol process using N-methyl-2-pyrrolidone. Aqueous ammonia solution have been used for removal of CO2 and H2S, particularly in the ammonia synthesis plant where ammonia is available. Water has also been used, but CO2 solubility is poor, requiring high pressure operation, and hydrogen losses because of the solubility are high. So for the adsorptive purification, fixed bed absorption can remove such impurities such as CO2, water, H2O, CH4, C2H6, CO, AR, and N2, among others. One type of process is the thermal swing process, in which the impurity is adsorbed at a low temperature and desorbed thermally by raising the temperature and passing a non-absorbable purge gas through the bed to aid desorption and carry the desorbed gas from the bed. For continuous operation, two beds are necessary. While one bed is on stream, the second bed is being regenerated. We have here the second type of process, which is the pressure swing absorption process, or the PSA, in which the impurities are adsorbed by a molecular sieve under pressure and desorbed at the same temperature but at a lower pressure. A purge gas may be used for continuous operation. At least two beds are required. Its principal advantages is that it can operate on a shorter cycle than the thermal swing process, thereby reducing vessel sizes and absorbent requirement. It is capable of purifying a typical crude hydrogen stream to a high purity hydrogen product containing 1 to 2 parts per million total impurities. So we have here the cryogenic liquid purification. An impure hydrogen stream can be partially purified by simply cooling to the appropriate cryogenic temperature, where the impurities will condense and can then be separated as a liquid stream. This is often used for bulk removal of light hydrocarbons from hydrogen in a refinery of gas. The product purity obtainable depends upon the vapor pressure of the impurity, and high purity are not readily attainable in most cases. Addition of purification, Lind removes low boiling contaminants in a hydrogen gas stream at 2.1 megapascal and 180 degrees Celsius by washing successively with liquid methane to remove N2 and CO, and liquid propane to give 99.99% hydrogen. Final purification employs activated carbon, silica gel, or molecular sieve. Low temperature for washing with liquid nitrogen or for fractionation are also used to remove impurities. And for the para-hydrogen content of both liquid hydrogen should be greater than 95%. The term ortho and para refer to the direction of nuclear spin in the hydrogen molecule. Hydrogen normally contains 25% para at room temperature but slowly converts to nearly pure para at liquid temperature. During liquefaction, hydrogen should be catalytically converted from the ortho to the para form to prevent subsequent exothermic conversion and evaporation of the product in storage. So the heat of conversion of 700 TJ is great enough compared with the heat of vaporization, which is 444 joule, to cause considerable loss. An interesting development is the use of semi-permeable membrane either to produce pure hydrogen or to adjust the gas stream composition. Hollow fiber of polysulfone covered with a proprietary coating or the Monsanto's PRISM system are used for the membrane. The separator consists of a bundle of fiber which has 10,000 to 100,000 oriented vertically that is kept at one end and placed on an open epoxy tube sheet on the other. The fibers are 800 micrometer in diameter or less and the whole vessel is 10 or 20 centimeter in diameter by 3 meter long. The separation of the component of the entering gas is determined by the rate at which the substance permeates the membrane. The modules can be run in series of parallel to attain high purities or to vary the composition of synthesis gas. One application is the production of 1.3/1 hydrogen CO gas for oxo alcohol manufacture from 3.1/1 hydrogen CO gas. And these are the references used in this lecture. And that's all. Thank you for watching this lecture and God bless.